Okay,
Yeah,
so
we can see
screen
your
is
screen.
visible. Yeah,
Yes, yes.
thank
Thank
you
you.
so much. So I'll try to cover some of the basic statistics. So first question, you can either write down in the chat box or write it down in your notebook. What type of variable is rupture of membrane more than 24 hours? This is a table of basic variables taken from a particular study. So rupture of membrane more than 24 hours. What type of variable is it? And how is it represented? Is the first question. Second question is same study, table 1, baseline characteristics. What type of variable is Apgar score? Apgar score. Third question. So the first two variables, one is gestational age in weeks. Second is birth weight in grams. Both are numerical variables. However, gestational age is represented as mean plus minus 1 standard deviation, whereas birth weight is represented as median and interquartile range. Why is it so? The fourth question is this particular graph, which represents the use of antenatal steroids for late preterm births, and the outcome discussed here is versus placebo. Outcome discussed here is need for any respiratory support. So what type of graph or figure is it? In this particular study, do you find antenatal steroids to be beneficial or not for late preterm? The answer can be just yes or no. So fine. So if you have not gotten it right, or you're still trying to figure out the answers, we will complete the presentation, and at the end of the presentation, if you get the answers, then you have understood. So the first objective would be to define what are variables, the type of variables, how we can express data, and how we can determine normality. This will be followed by a brief discussion on risk ratio and odds ratio. Finally, we'll discuss something about the systematic review analysis. So variable is a quantity, or anything which varies from individual to individual, like blood pressure, age, weight, blood group, stage of disease, presence or absence of a particular disease like diabetes, hypertension, etc. So we can classify variables as qualitative variables which describe the characteristics, or quantitative variables which can be counted. We also have independent or input variables and dependent variable or output variable. For example, salt intake is an input or an independent variable, but what influences the salt intake influences the outcome of blood pressure. So here the blood pressure is a dependent variable or an output variable. So variables can be classified as categorical or qualitative variables, which are further classified into nominal, ordinal, and numerical variables, which are discrete and continuous. Nominal variables are named variables. They are mutually exclusive and unordered. Blood group, various types of blood groups, married, widowed, single, etc. So these are nominal variables. Now, they can be either binary or dichotomous. For example, when you have only yes or no, or two answers, only two possibilities for that. So then it is called binary, yes or no answers, alive or dead, presence or absence of a disease. Whereas you also have polynomial scales where you can have more than two options. For example, blood group types or ethnicity. They are polynomial scales. When you can bring in some order, then it is called as an ordinal variable. For example, the grades of hydronephrosis. So no hydronephrosis, then you can have mild, moderate, and severe. So you can similarly replace this characteristic as none, mild, moderate, and severe as 0, 1, 2, 3. It would still retain the meaning, and then you can have an order. So similarly, pain scale, visual analog scale for the degree of pain, you can have it as none, mild, moderate, severe, or you can put in a number and categorize them. For example, anything above 7 is called as a severe pain. So you can either grade it or you can either grade it or give it a number. But here it is a qualitative variable, but it can be ordered. That is an ordinal variable. Now coming to numerical variables, they are discrete and continuous. Discrete is, it can take only a whole number value. For example, number of episodes of diarrhea, vomiting, number of live births. So they can have only discrete or whole numbers. So they are called discrete variables, whereas continuous variable can have any decimal point, but still it will make a meaning. For example, height 123.53 centimeters, still it has a meaning. Similarly, weight, blood pressure. So these are continuous variables. They can take any value within the specified range. So now what type of variable is Apgar score? What type of variable is Apgar score? Isn't it? So here there is only an order. So it is an ordinal variable. Just that it is again qualitative variable, ordinal variable. The only thing is that there is a number to it. There is a number to it. So an Apgar, why it is not a continuous or a numerical variable? Because Apgar of 3 is not exactly twice as bad as an Apgar of 6. You can replace these numbers with anything, but still it will retain a value. So Apgar score is a ordinal variable because there is an order to it. Because it is a number, the people generally represent it as a median and interquartile range. Temperature scale, centigrade or Fahrenheit. So there is an order to it because we can have temperatures from 0 or minus and up to any degrees. The interval between two values is the same. 0 is arbitrary. Why 0 is arbitrary? Because a temperature of 0 does not mean absent temperature or 0 temperature. 0 is only an arbitrary. There is still some thermal value to it, but 0 is arbitrary. So it is an interval scale. It is a numerical variable, but it is an interval scale. Other examples of DQ score, IQ score, they are all numerical, but interval scale variables. So now variables can be nominal or named. Ordinal, there is named, and it is ordered. So the name can be mild, moderate, severe, or you can even give a number here. Interval is, there is a specific interval, equal interval between, specific interval between two variables, and 0 is arbitrary. Ratio is, it is ordered, proportionate interval between variables, but 0 has a meaning. So almost all numerical values are in the ratio scale. We can add, subtract, divide, still the data will retain meaning. However, in general parlance, nominal and ordinal, they are considered together. They are qualitative data. Interval and ratio are expressed similarly. They are numerical data. So now let us see how data can be expressed. So nominal and ordinal both are categorical variables. So here generally the expression is in the form of number and percentage. So if you had looked at the first question, rupture of membranes more than or equivalent to 24 hours. So the answer is either yes or no. So if the S is represented as number and percentage. So most categorical data are expressed as number and percentage. However, when you have some ordinal data and it is in the form of number, then you can have median and interquartile range. Stages of cancer, stages of a disease, they can all be expressed as number and percentage. So this is the common type of expression. So we have discussed answer. Now coming to numerical data. So both interval and ratio, they are expressed similarly. So whenever we express numerical data, there are two things that we need to tell about this. What is the central variable? How is the dispersion of the variables around that central point? So for that central point, we use measures of central tendency, either mean, median, or mode. And the spread of the variable is expressed as standard deviation, range, or interquartile range. So for example, we have 30 babies and we want to express the weight of these 30 babies. So this is in the form of a table. Here it is in the form of a bar diagram. Now, how do we express it? One, we have to express where the center is and then the dispersion. So find out where the center is. We can calculate mean. Mean is all the variables added together divided by the number of observation. So which is 30 babies. So here the mean is 3,155 grams. To describe the spread, we can have the minimum value and the maximum value. But what we generally use is standard deviation to depict the dispersion of data, which will give more information than just telling about what is the minimum and the maximum value. So how do we calculate standard deviation? Suppose this is the line, each data point, how far it is away from the mean. So some are in the positive direction, some are in the negative. So we find the difference, then we square it. So when we square it, the differences, whether it is in the positive or in the negative direction, they get cancelled. So then we take the square it, add all of them, divided by n-1 and take the root. So root means square. So in this example, the standard deviation is 499, right? So for mean, whenever we discuss mean, we use mean and the standard deviation. Standard deviation discuss the spread of the variables. Another way to look at it is to find out the median. So how do we find the median? Median is the central point. So arrange the variables in ascending or descending order. Find out where the central point lies. So here 3090, that is the median. So this is the point which has half the values above and half below. Now we can also divide the entire data set into 4 equal halves. So this is the middle half. This is the first quartile, second quartile, third and fourth. So if you tell us the middle half, then this stands for interquartile range. So here we have the 25th centile and here we have the 75th centile. So whatever is in between is the interquartile range, 25th and the 75th. So in between is the middle half, which is the interquartile range. So this can also be represented in the form of a box plot. So whenever you have a box plot, understand that it is median and interquartile range. The middle line here represents the median. Lower margin of the box is the lower quartile. Upper margin is the upper quartile, which is the, here it is the 25th. Upper is the 75th. And this whisker, it represents the minimum and the maximum values. So box plot provides a lot of information. For example, in this particular study, which had used procalcitonin in patients without infective endocarditis, and those with infective endocarditis, you have a box plot. This central line is the median. So from here we understand that the median value is around 6. The 25th percentile is 2.57 and the 75th percentile is 12.48. These are the minimum and the maximum values. So that's how from the box plot we can understand, derive lot of information. Now the question is, why certain numerical values are represented as mean standard, whereas some others are median and interquartile. So the first thing that we need to understand is, if the data is normally distributed, it will be represented as mean and standard deviation. But if the data is skewed, then we use median and interquartile. So what is normal distribution? Normal distribution is a distribution where all the data points in a data set are symmetrically distributed around the mean, and the distribution takes the form of a bell-shaped curve. So here mean, median and mode, they are all the same. Whereas in a skewed distribution, we have large numbers of values to one side. We have more values here. So the distribution is skewed. Here median and the mean are far away from each other. Mean is influenced by outliers. If we have one value which is very high, the mean will be pulled towards that. So we have a lot of information from this standard deviation. What is the characteristic of a normal distribution? Normal is written with a capital N. It can be described by two parameters. One is mean, second is standard deviation. In a normal distribution, the distribution is bell-shaped and it is symmetrical about its mean. Mean, median, mode, they are all the same. So when you know one standard deviation, we can say that 68% of all data points are going to lie between -1 and +1 standard deviation. 95% of all the data points will lie between -2 to +2 standard deviation. Within 3 standard deviation, almost all data points would lie. So why determining normality is very important? Because we can express data as mean and standard deviation. And when the variables are expressed as mean, standard deviation, we can use more robust statistical tests when we compare two groups or something. So how do we determine normality? We only will have the values, mean, standard deviation. So looking at that, how we can decide whether the data set is normally distributed or not. In real life, no data set will be exactly normally distributed. However, we have 3 common ways of finding out. So one is a rule of thumb. Second is we can look at some graphical methods. Third, we can have some statistical methods. So one rule of thumb is, when the sample size is large, the data tends to be normally distributed. For example, you have a study with sample size of just 20. Compare this with the sample size of 500. So it can be just weight or it can be just age. So when the number becomes higher, it is approximately normally distributed. So a large sample size likely to be normally distributed. Second, look at the mean and the median. If they are far away from each other, then it is slightly skewed. Third, look at the mean and standard deviation. If the standard deviation is more than half of the mean and negative values are meaningless, it is likely to be skewed. So we'll look at this example. In this, just look at the mean 2 and standard deviation 0.17. However, in this, You have mean 1.67 and standard deviation is also 1.5. So more than half the mean, it is a skewed distribution. So graphical methods, we can draw a histogram, look at it. So here, this is a skewed distribution, tail to the left, here tail to the right, it is a skewed distribution. We can also look at the box plots. So here it is a normal distribution, even though you have used a box plot, putting the mean and the interquartile ranges. How this box plot differs? It is a symmetrical box plot. Whereas this here, this is the median, interquartile ranges. So look at the box is not symmetrical about the median. So this is a skewed distribution. Again, this is a skewed distribution. So here, what distribution is? This is again a skewed distribution because the box is not symmetrical. So rightly, the authors have used median and interquartile range to represent this particular variable. So you can also use certain statistical methods. One among them is a PP plot, which can tell us which type of, whether the data is normally distributed or skewed. So in summary, when we have a data which is normally distributed, we would use mean and standard deviation. If it is skewed distribution, median and interquartile range. So this is the summary of the variables that we have discussed so far. So we have discussed the 4 types of variables: nominal, ordinal, interval and ratio. Nominal and ordinal come under categorical variables or qualitative variables. Interval and ratio, they are handled similarly. They come under numerical or continuous variables. Here we have examples. Normally distributed numerical variables are expressed as mean and standard deviation. 68%, 95% and 99% of subjects are captured with plus or minus 1, 2 and 3 standard deviations respectively. Whenever we have a skew distribution, we express as median and interquartile range. And I also told you some of the rules of thumb and graphical methods to identify whether a data set is normally distributed or not. Okay, when we use mean and standard deviation, we can have robust statistical methods like the parametric test for analysis. So when the data is skewed and you have median and interquartile ranges, then we use non-parametric tests to analyze them. Now we will talk about odds and risk. Can we proceed further?
Yes, Dr. Sindhu.
Sure. So odds and risk. So now, please look at this particular outcome table. So in this study, authors have compared CPAP using 2 different nasal interfaces. One is Ram's cannula and other is Hudson nasal prong. So there are some variables. One is need for mechanical ventilation. What type of variable is it? It is a yes or no variable. Did the baby require mechanical ventilation or not? Yes or no. So this is a categorical variable. So how is it represented? It is N and percentage. Change of interface, requirement for a need for change of interface, again a categorical variable. Whereas duration of CPAP in hours is a continuous variable. Infants who remain on CPAP by 3 days, again in categorical variable. Duration in days, numerical variable. CPAP failure is a categorical variable. So when you look at the categorical variables, all are represented as N and percentage, right? N and percentage. Whereas your continuous variable, this is a skewed distribution. So it is expressed as median and interquartile range, right? Again, duration, median, interquartile range. So that's how we can figure out why they have used. So it is a skewed distribution, so they have used. Now, when you compare 2 groups, you can either use risk ratio or mean difference. Risk ratio is used when the parameter or the variable that you are discussing or analyzing is a categorical variable. So here, mechanical ventilation, change of interface, infants who remained on CPAP, CPAP failure, all these A, superscript A, they are all categorical variables. Here they have used risk ratio. So they will all be as risk ratio and 95% confidence interval. However, look at these numbers B, these are numerical variable. When you compare numerical variables between two groups, we use mean difference and 95% confidence interval. Here you have the p-value. Now let us understand what does this risk ratio mean. So this is the same example. Now let us assume that we have 20 babies and we have randomized them to receive CPAP using Hudson, prongs or the Ram's cannula. Here our primary outcome is need for mechanical ventilation or intubation within 72 hours. So in this Hudson group, among 10 babies, 2 required ventilation or 2 failed the therapy. So here in Ram's cannula group, here 3 of them failed the therapy. So now let us calculate the risk for mechanical ventilation in the 2 groups. When we calculate risk, we put the risk, those who required mechanical ventilation divided by total number of all babies in that group. So all the green ones, those number who failed. So the denominator will include those who failed also. So total number is 10, 2 failed. So 0.2. So the risk for failure is 20%. 2 out of 10 will fail. So in the Ram's group, 3 failed out of total 10. So 3 out of 10, the failure percentage is 30%. Now when I tell 20% risk of failure, 30% risk of failure, you will be able to get a mental picture, understand it better. Now, relative risk is the ratio of 2 risks. So you put the ratio of failure in Hudson group divided by the ratio of failure in the Ram's cannula group. So we got 0.2 divided by 0.3, which is 0.6, right? 0.6. So what do we understand? The relative risk of failure in the Hudson group compared to CPAP or whatever it is 0.6. So 0.6 is, so 1 is if it is 100%, 0.6 means the CPAP group is 40% less likely to need mechanical ventilation compared to HFNC. So what do we understand? Risk ratio is the ratio of 2 risks. We calculate the risk of that outcome. It can be a positive outcome or a negative outcome in both groups separately. And then we divide. That is called as risk ratio. If the risk ratio is 1.2, so 20% higher risk for failure. If the risk ratio is 0.8, 20% less likely to receive or fail. That is the implication. So here CPAP failure. So 0.91, 0.82 to 1. So confidence interval, 95% confidence interval crosses 1 or touches 1. So it is not significant. So the failure less likely to fail in the Ram's group compared to Hudson group. So there is a 9% less chance to failure, but it can range anywhere from 18% less risk for failure to no difference at all. So when it crosses or touches 1, 95% confidence interval, the p-value is not significant, which means that this observation may be just due to chance alone. Now, what do we understand by odds? Odds ratio is the risk of failure, so you do not include those who failed in the denominator. So 2 of them fail divided by those who have succeeded. So 2 divided by 8. Here in the same way, 3 divided by 7. So it is less intuitive. Odds is generally used in betting. In studies, clinical studies, odds are used when the disease in question is very rare. So again, similarly, odds ratio is the ratio of 2 odds. So it is less intuitive to think with the odds ratio in mind. Generally, risk ratio, when you present it, it is very easy to understand. So generally in case control studies or when the disease in question is a bit rare, odds ratio is used. Now let's discuss something about the forest plot. Now this particular figure is the forest plot, the one I showed earlier. So we will discuss about this particular figure in detail. So when do we use forest plot? For example, you have done a number of randomized control studies, and each one of these studies provides you with an RR and a 95% confidence interval. Now you want to put all these studies together and find out one particular summary point. So you need to gather information from all these 5 or 10 studies. Some studies tell that it is beneficial, whereas others say it is not beneficial. But you want to understand what is the final take home from all these studies combined. So then you do a systematic review, collect all studies which answer your particular research question, collect the data, and then you put the data together and analyze them. So not all systematic reviews would result in meta-analysis. Meta-analysis is the final combination where you compile all the data and finally arrive at a summary point. Systematic review is the initial process where you do systematically data search, collate, and answer the questions. So here, you have done a meta-analysis. The meta-analysis here, what is the outcome? Outcome here is need for any respiratory support. What type of outcome it is? It is a categorical variable, yes or no, categorical variable. So here you have the study, here you have the events. Need for support 6 out of 96. So the events in the antenatal corticosteroid group, then you have in the control group, and each study provides you with a risk ratio 95% confidence interval. And finally, you get this particular figure and the diameter. So we will analyze these graph in detail. So here you have the line of null effect. So if it is a risk ratio or an odds ratio, this line will be 1. If you have a numerical variable and you are representing it as mean difference, then this number will be 0. If it is mean difference numerical variable, it will be 0. Whereas it is a risk ratio, it will be 1. So this is the line of null effect, and you have the horizontal axis. And each study will be represented with a central point with 2 arms. So the central point is the risk ratio, and the 2 arms are the 95% confidence limit. So each study gets plotted on this particular graph. So sometimes it may favor treatment, sometimes it may favor control. So, but when they cross the line of no difference, then it is non-significant. So putting it all together, so now 1, 2, 3, 4, 5, we have 5 studies, each one with a different risk RR and confidence interval. And then finally, the diamond. So here what we need to understand is the size of each study is given a weightage. This weightage depends on 2 things. One is the sample size of the study. Second is the number of event rates in the study. For example, if this was mortality, this study had a very large number of participants, greater sample size. That is why 95% confidence interval is narrow. And they also had a higher event rate. So this study is given a greater weightage compared to other study. Now, what do we infer from this study? This is a small sample size study. Although it showed lesser mortality, look at the confidence interval, which is very huge. So small study, less event rate, very wide confidence interval. So the study is given less weightage. So that is why the box size varies, because of the sample size and the event rate. So look at this large confidence interval, and so the study is given less weightage. So finally, we have the diamond. So looking at the forest plot in detail, here we have the number of studies. So here the second section tells about the event rate and the sample size in each arm, right? So not sample size, the number of participants in each arm. So here the event rate and the participants in control arm. So we will get a number, and finally we have the total number event rates as well as the total number of participants in each of the arms, 2 arms. That is what is understood. And third one is a depiction of each of these. For example, as I told, this study had a large sample size. Look at this particular study. It has a very large, big thing. So even the sample size is high, event rate is also high. So look at the number here. So, so we have a higher number of participants, 131, 137. So it has a higher weightage here. So this is what is represented in numbers. 0.71 is the risk ratio and 95% confidence interval. Look at this confidence interval crosses 1. Therefore, it is 1.31. And the final diamond lies to the left, 0.77. Confidence, the edges, these are the 95% confidence interval. They do not cross 1. So see 0.67 to 0.89. So if it is in bold, then it is significant. It's some are depicted in bold just to say that it is significant. So one more thing that we get at the end of this forest plot is the heterogeneity. Heterogeneity, which is depicted by the statistic I-square. Preferably, we want the I-square statistic to be less than 50%. So in this example, it is 38%. If it is above 50%, then it just implies that the studies that you have collated together have heterogeneity. Heterogeneity, they are variable, but we don't know in what way they differ from each other, whether it is with respect to the dosage of the drug or with the sex of the population or some other thing. So it just depicts that the population or the studies that you have put together to derive a meta-analysis, they are heterogeneous, which you need to look at. So in effect, the symbol of Cochrane is the forest plot. Here you can see the central line, the various studies, and then the diamond. And in fact, this is derived from the first ever meta-analysis done in 1973, which is the effect of antenatal corticosteroids for preterm births. So looking at our figure, name the figure. This is forest plot. Is antenatal steroid beneficial or not? Look at the diamond. So it is 32% reduction in the need for any respiratory support. Look at 95% confidence interval. It is significant because it is not touching 1. But what is the implication? The reduction can range anywhere from 53% reduction to just 2% reduction. So statistical significance does not mean clinical significance always. So when you give antenatal steroids to late preterm birth, you can have a reduction in any respiratory support from 53% to just 2%. So whether to take it or not is up to the clinician. So I think with this, these are the things that I had used for to cover the statistics part. But if there are any questions, I will take up the questions and then explain.
Thank you, Dr. Sindhu. I think it was, even though it was basics, you explained so clearly. I'm sure everybody's basics have got a little bit strengthened. So any questions are there? We can like take questions for 10 minutes or so. Dr. Sindhu, can you see the questions in the chat box?
This asked, what is the diamond in the forest plot? It is the summary statistic of the final risk ratio and the 95% confidence interval. How do we calculate it? There are some statistical analysis which can help us to calculate the final RR and the 95% CI. Significance of p-value, generally we accept a 5% chance whenever we compare two groups, right? And you find a difference. So it is possible that it is due to a chance of finding that there is any difference between the two groups. Okay, if the percentage by which it is due to chance is 5% or more, then you wouldn't take it as there is any difference between the two groups in truth, right? If it is less than 5%, which is p-value of less than 0.05, so then the difference between the two groups is more likely to be true rather than by chance. So to understand this clearly, we need to understand the null hypothesis. Then only we will be able to understand this p-value. But in simple terms, it is the percentage of chance. So we didn't cover this sensitivity, the test characteristics, which is sensitivity, specificity, because these took up a lot of time. I didn't cover, although I had one ROC curve,